All right, I think we'll start about here. Seems like a good time. Adjust some of this stuff. Don't need any more music. Okay. Um. So yeah, if you do have any questions you want to go over specifically, you can either put them in the chat or in the Discord. There's a Wednesday section for problems. So yeah. Let's see. Really didn't. I'm not really sure which problems I want to go over specifically. So last time we were on Tuesday yesterday, we were doing complex line integrals. Right, so this is the beginning of chapter 2 in this book, I believe, right? Yeah, 2.1. A couple of the main points from the section were if we had a holomorphic function defined on some open set, u, and if the holomorphic function had an antiderivative, so if there was some function that's holomorphic f of z such that the derivative, a holomorphic derivative is equal to like some other function, little f, for every point. Right, then we had sort of like a complex fundamental theorem of calculus that said if I take any closed integral in that domain, so some line integral that starts and ends at the same point, then I can use the antiderivative and the fundamental theorem of calculus to say that the value of the integral should just be the endpoint, the function value at the endpoint minus the function value at the beginning point. So just f of some number minus itself. Right, so any integral for little f should be 0, any closed integral. Along any curve, dz should be 0. Okay, so this is sort of like our shortcut to skip ahead for some of these problems, right? If you get a problem and you know that the function has an antiderivative, then you know if it's a closed line integral, the integral is automatically 0. So it sort of saves some time, especially if your contour is sort of difficult or if it's piecewise linear and it's made up of a lot of different pieces. This calculation can be hard to do by hand. So it can be good sometimes to have a theorem that says in certain circumstances that integral's just automatically 0 for theoretical reasons. Okay, so I don't know. I'm looking through some of these problems right now. Let's see. Let f be holomorphic on an open set U. Interior of a disk of a rectangle. Right. Okay. Huh. So yeah, let me go over this first problem. We can sort of speculate about what they want us to think about with this one. But yeah, if anyone's just joining, we're going over problems on the board. So if you have a problem you want us to go over, then put it in the chat or the Discord. But yeah, currently we're just going over some complex analysis problems. Okay, yeah. Let me just stick with this marker for now. Okay, so this is a similar problem to this picture I was just describing here. Problem 1 says, this is page 60. So let f be holomorphic. So I'll write holomorphic this way, holomorphic on U, just notation. Where U is the interior of a rectangle. Okay, so U is the interior of some rectangle. We could draw it maybe like this, right? So what they're saying here is that they want us to calculate this integral starting at just some closed curve. So we start and end at the same point. So let's say we're going counterclockwise, I think. Or I guess it doesn't really say. Yeah, let's just say it's counterclockwise. Yeah. Oh, no, actually it's the interior of the disk. Okay, so gamma is just some function 0, 1 to the inside of this set. So it's just some closed curve like that. I thought they were gonna have us integrate like around the boundary of the rectangle, but I mean, it doesn't really matter. So any homotopic curve should have the same value, right? So if this curve is homotopic to the boundary of the rectangle, well, I guess you have to make sure the function's actually defined on some, you know, it has to contain the boundary of this set that we're integrating over. But okay, yeah, I guess the hint sort of gives it away. I should have probably read the hint first. It says, recall that f has a holomorphic antiderivative. So if we're assuming it has a holomorphic antiderivative, then that's essentially what we were just saying before. So the integral around this closed curve, if this is gamma, right, there's some holomorphic antiderivative. So the derivative of, so the integral of f of z dz is just that holomorphic antiderivative, capital F, at whatever the start point is, which I'll call z naught, minus itself, which is 0. Okay, so the main point of this problem is to make sure that you understand that if you have a holomorphic function defined on an open set, which is the interior of a rectangle, that means it's simply connected. And that means that we can define a holomorphic antiderivative on the entire open set U. So that means that this capital F is the antiderivative, its derivative is little f, and we can use the fundamental theorem of calculus to say that this integral must be 0. So that's the first problem. Yeah, so a lot of these problems are similar in the sense that they have to do with topology. Remember, we were talking about if we have two homotopic curves, then they always have the same integral, right? So you can sort of think of the simply connected notion as saying we can squish this entire curve down to a point, and then if we take an integral over just a single point, that's always just 0 because there's no there's no length to that, right? It's basically not an integral at all. You're like adding up nothing. So yeah, the whole point of a simply connected domain means that any integral that's like a closed curve like this, we can actually just shrink it down to a point. So the integral is equivalent to the integral over a point, and the integral over a point is just 0. The only time we can't do that is if the function, like yesterday, is not defined at some point in the middle of the curve. Like 1 over z had a problem in its definition at 0. So then there's no way to shrink the closed curve continuously to a point without having to break the curve at some point. So that's, yeah, that was that issue we were talking about yesterday. Okay. Let's see. Oh, I don't even know if I have the Discord even open. That's not good. Okay, so let me open the Discord, see if we have any problems. If you're just showing up and you want us to go over a problem, drop it in the Discord. We have the Wednesday exercises submission section. So yeah, that's the spot to share your problems. Share all your problems with the world. Okay, let me see. What else do we have here? Number 14, if f and g are C1 complex valued functions on an open set U, and f prime and g prime exist on U, and if f prime is equal to g prime for all values in U, then how are f and g related? Okay, that's That's actually, I think that's an interesting problem. Let's think about this one for a little bit. Okay, so number 14, this is page 62. So if f and g are C1 valued functions, complex valued functions, okay, so this just means, so if f and g are continuous on u, so they're continuous at every point of view, the derivative exists at every point of view, and the derivative is also continuous. And they take values in this two-dimensional real space, which we call the complex numbers. So if so if this is true on u, and if f prime and g prime exist on u, so and if f prime of z equals g prime of z on all of u, so basically we're assuming these two functions are complex valued, they're continuous, their derivative is continuous, and the derivative exists at all the points, and they're equal. I guess when they say f prime and g prime, I think they mean the complex derivative exists. So it's not only C1, but it's holomorphic, and the derivatives exist and are equal to each other for all points z. Then how are f and g related? That's the question. Okay. Any questions about the question? Right, so we have if f and g are C1 of u complex valued functions, and if the derivatives exist at all points and are equal to each other, then how are f and g related? That's the question. So I think the point of this problem is to think about your one variable real case, like when you had two functions in the real case that were equal up to a derivative, right? This is sort of like, how antiderivatives, we say, you always have to add plus c, right? So I think that's what they're sort of getting at here. If the derivatives are equal, then, we know the functions don't necessarily have to be equal, because, the constant function, if the constants are different, then they're not the same function, but their derivatives are the same, right? So, yeah, I don't know. I don't see anybody in chat, but yeah, I think the main point of this problem is that, basically, if two functions are equal, we want to show that they're equal up to a constant. So f of g should be equal to f of z should be equal to g of z plus some constant c, which is, I guess, a complex valued constant in this case. So how do we prove that? I'm actually not. It's probably not too hard. I mean, I literally haven't really thought about it at all, but I don't know. Maybe somebody in chat can start us off with some sort of direction in how to prove this. I'm also a little unsure what they mean by f prime. Are they talking about I think they just mean df dz, like the holomorphic derivative. Yeah, that would make sense. Oh, wait, actually, maybe they mean something more general. F prime and G prime exist on U. I'm guessing they mean that the df dz bar is 0, but I'm a little unclear with the way they're wording it. Yeah, okay. I think we're just assuming that yeah, I'm not really sure actually. Set. Oh, okay. I think I see. Right. Right. So if the derivatives exist, then we can define an antiderivative using the integral, maybe, or so they just differ by a constant. Yeah. So we're trying to prove that. I'm just trying to make sure I understand what's going on with the actual statement of the problem. I think we're just assuming here that this is like df dz. So df dz is equal to df gz. Sorry. Yeah, dg dz. Yeah. Okay, so hopefully people understand at least what the problem's asking. Now we can try to solve it. So the derivatives are equal. We want to show the functions are equal up to a constant, basically. So let's see. So yeah, let's just write down what we know already. Okay, so we have some set U here. And we know that f and g are C1 and their derivatives are equal on this function, or on this open set. Okay, maybe we can look at like f minus g. We want to show f minus g is equal to some constant. Right, and then we can always define, if we know that the holomorphic antiderivative exists, we know that it's defined as the integral from some fixed point. I can just define it at any point, z naught, and I can take the integral to some point z. And we know that these are equal for both f and g, because the derivatives are equal. So I can take the I know that f of z is equal to an integral from, any path from z naught to z of f prime of z dz. But because the derivatives are equal, this is also equal to the integral of g prime. Right. So, oh, wait. Oh, yeah. So this is equal to what? Yeah, so this is equal to g of z minus some constant, which is g at the original point. Yeah, okay. And this is a constant. Okay, so f is equal to g minus a constant or plus a constant. Doesn't really matter. We can rearrange things. Plus c minus c. It's all all the same, but the point here is that f minus g is equal to a constant. So f is equal to g plus some constant, in this case minus. Plus a minus constant. Okay, does anybody have any questions about that one? So we assumed that the functions had the same derivative, and then we wanted to show that they're equal up to a constant. We know that I can always write a function as an integral of its derivative from some fixed point to z. But because the derivatives are equal, this is also equal to this integral, and this is, by fundamental theorem of calculus, this is just a difference of g at 2 points. Okay, so f of z, oh wait, actually, I think I'm messing up here. Yeah, I guess maybe we should say that this is, really, this is f of z minus, yeah. Nobody called me out. Right. And now I can move this to the other side, right? So, yeah. And now this whole thing is a constant. Right, so f is equal to g, minus this thing plus this thing, but everything on the right is just a constant. Okay, any questions, guys? So we assume the derivatives were the same, and that means that the functions are equal up to some. We have to adjust for whatever the value of the two functions was at this original point. But because the derivatives are equal, we can sort of like integrate along any curve to get to z, and we should get the same number. It's just a matter of the functions might differ at this original point that we started at. So yeah, Rex, they just differ by this stuff over here. Okay, so that's 14. That one was pretty good. They're basically just testing our knowledge of, if I know a function has a derivative, what's the integral of the derivative? Fundamental theorem of calculus says it's the difference of the original function at the 2 points. And they're also testing us to our understanding of whether we know that, we can always find this antiderivative using this method of integration along some path. Should I do one of these complex line integrals? Probably. Yeah, let's do the first one. It's probably not too difficult. Any other problems, guys? I'll keep looking in the Discord, but I don't see anything yet. I'm not at the normal scheduled time, so that's probably my fault. A little bit early, but hopefully people stumble in and... Oh, Jake's question, right. Oh, I don't even know if Jake is Jake even here? Maybe we could wait if Jake shows up later. Yeah, I'll do Jake's question, but kind of want to save it for if he's actually here in a bit. I think he usually shows up on Wednesdays, so he might show up in like 30 minutes. Okay, so let me just do one more from the complex book here. This is problem 18. Right, so this is an integral, closed line integral again, along some gamma. This is, I'm really bad at these. Is that, how do I do this? Is this a zeta? Yeah. Is that it? Sort of. I haven't done this in a while. There we go. That was better. D zeta. That's a really bad... Each one is different. Okay, so gamma describes the circle of radius 3 with center 0 and counterclockwise orientation. So let me just draw a quick picture of gamma. Center 0 and radius 3. So this is like 0 plus 0i in the middle. Okay, yeah, that looks good. Let's see. Okay, so the problem here, this is similar to the question we were looking at yesterday where there was a hole where the function wasn't defined, right? There's a problem at, zeta equals 1, we can't integrate, or the function's not defined at 1, but luckily we're integrating around the function. So we're actually missing the point where it blows up, but we're integrating around it. So yeah, the hole is like somewhere over here, right? But yeah, I think we can just do this one by hand. So we can parameterize the curve gamma by, oops. Let's put the parameterization over here. So gamma of t, I don't know why I can't write gamma all of a sudden. So this is 3 e to the I t, and t is going to go from 0 to 2 pi. This just parameterizes our, circle of radius 3, going around the outside once. Okay, and then remember from yesterday, how do we define this integral? We have to find a parameterization first, and then we have to do a chain rule for the d zeta part. So this will be an integral from 0 to 2 pi, which is the bounds of our parameterization here. And then for zeta, we're going to plug in 3 e to the it squared, and then divide by, 3 e to the it minus 1. And then when we multiply, we get a little bit of an extra term here. So we get the derivative of this dt. So 3i e to the it dt. And then a bunch of stuff cancels, maybe? No, almost. So how do we simplify this now? Because I'm probably going to run out of room in about 30 seconds, but... okay, so 3 e to the it, so that's the top part, that's zeta squared. 3 e to the it on the bottom minus 1, and then we have the derivative here. Okay. So we're sort of guessing that the integral is probably not going to be 0 since this function isn't holomorphic on the entire interior of the boundary. And also the power on the bottom is 1, so sort of thinking that that's probably the case, but yeah, let's show that it's true. Maybe I could have just done a shift real quick. Yeah, no, that would still make it awkward. Just trying to find the fastest way. I guess we don't want this denominator, right? That's kind of annoying. Huh. What do we think, guys? So yeah, we want to solve this parameterized integral. So once we parameterize it, now it becomes complex line integral, but just normal dt here. Yeah, so we're just basically integrating the real part and the imaginary part separately. But right now it's kind of hard to see that because we have everything in this e to the it notation. Grab my water. Okay, so we have a lot of e to the it's on the top. E to the it squared times e to the it. It's kind of hard to cancel it because this minus 1 on the bottom is making our life difficult. Trying to think of how to get rid of that. What difference is squares? Huh. I don't know why I'm stuck. I thought the first one would be easy. Probably is easy. I'm just confusing myself. Zeta squared. Huh. Might need some help. If anyone's in the audience. I mean, if this minus 1 wasn't on the bottom, that would be nice. So, I mean, usually we want to multiply by like, you know, the conjugate or something, like 3e to the it plus 1 or something on top and bottom. But I don't really think that helps us much. 1 is less than 3, z0 is inside, so we can use Cauchy integral formula. Yeah, but this is before we're not using Cauchy integral formula. We're supposed to do it without the formula. Yeah, I mean, this is like a Cauchy integral formula, right? Like, but yeah, I mean, if we just use the formula, that's sort of defeating the purpose of the problem, I feel like. Cauchy integral formula. Yeah, we'll go over the Cauchy integral formula on Friday. I'm pretty sure. Yeah, that should be like the main study for Friday. But this is like a preparation for that. So we're trying to do that before, or we're trying to not use that theorem. That theorem's sort of too strong here. We're trying to figure out what the value should be. But just by definition, just by plugging in the parameterization. I think. I mean, unless I'm thinking of this wrong, right? This is before. Yeah, I'm pretty sure this is before they even mentioned the Cauchy integral formula or theorem. So what is this supposed to be according to the formula though? Like 2 pi I times the value of the function at 1, so just 1. So just like 2 pi I or something. 1 or 1 squared, I guess. Yeah. Yeah, so it should be something like 2 pi I, right? But we want to show that by hand. Why am I so stuck on this? Huh. 2 pi I. Yeah, but how do we show it by definition here? How do we show that this is... So yeah, we have an I here. We can pull the I out. Very good. Can we do some sort of change of coordinates? Okay, maybe that's the way to do it. Yeah, let's do a change of coordinates. I think that's probably... Yeah, let me... actually, does that help? I want to just add 1 so that this on the bottom, like we can change coordinates, call it like W. W is zeta minus 1, and then it'll be something over W, right? dW. But the problem is that the parameterization gets weird. Sort of, not really, I guess, actually. Okay. Yeah, let's do it that way. Okay, so it'll be very similar, but we're going to do a shift of coordinates. And then our parametrization is also going to change a little bit. All right, so the old integral was integral from zeta squared over zeta minus 1 d zeta. We're going to change coordinates, so this should be equivalent to a integral over a similar path, or same path really, yeah. And it will be w plus 1 squared over w dw. Okay. Yeah, and then this new integral, so this will be an integral from 0 to 2 pi. 3 e to the I t plus 1 squared times 3 e to the I times I e to the it dt, which is the derivative. And then the bottom is just w, so the bottom is just, oh, wait. No, hold on. What did I do wrong here? Oh no, this is still just... No. Oh, wait, what did I do wrong here? W plus 1, this doesn't help us at all, does it? Just a shift. Yeah, that's the same. That'll just give us the same equation, I think. Partial fractions? Or no, what's the... Oh, maybe we can just split it? Is that one way? How does this split as a fraction? It should split as, like, you know, a over zeta minus 1 plus some polynomial, right? Of degree 1, I guess. All right, so let me just divide this out real quick. This is zeta squared. I wish I wasn't using zeta. I'm just going to use z for a second. So z times this gives me z squared minus z, which gives me minus z left over. So minus 1 minus z plus 1, so remainder 1, so it's z minus 1 squared. Yeah. So this is really z minus 1 plus 1 over, or zeta, whatever. Yeah, there we go. There we go. Okay. And then the calculation is very similar as the one we did yesterday. So you know it's an integral, so it splits as a sum, and then this part is 2 pi I, and the integral of the other part has a holomorphic antiderivative, so the other part has integral 0. So this is really just like 0 plus 0 plus 2 pi I. And the calculation for this one is very, very similar to yesterday. Right each term. You can try expanding out the numerator. Is that what we did here? I think this is right? Then integrate normally, which would be w plus 2 plus w to the... Did I do this wrong? Oh, you're doing it from here. Right. Yeah, exactly. Yeah, that's I think what we did, but just in the original coordinates. Yeah, we didn't need to change coordinates. I thought we had to, but we didn't really have to. So yeah, this integral splits as a sum of 3 integrals, right? Where the first 2 are 0 because these functions are holomorphic and they have a holomorphic antiderivative. Or sorry, it's only because they have a holomorphic antiderivative, and then this one doesn't, but we know its integral is this 2 pi I because we calculated it. Something very similar yesterday. Substitution. Okay, yeah, I mean we can solve this one too, but we know that the first 2 are 0, right? Okay, yeah, let's just solve the other one, I guess. First 2 are 0 by fundamental theorem of calculus. These two have antiderivatives. So let's show that the 1 over zeta along this curve is 2 pi I. Is that even easy to show? I don't know. So it'll be 0, 2 pi, 1 over e to the... Yeah, e to the it, or 3 e to the it. Yeah. And then times... Oh, okay. Yeah. This is the same proof as yesterday. Yeah, sorry. 3I e to the it dt. Right, and then the 3's cancel. You can pull the I out. Right, so this is really just 0 to 2 pi. 1, the e to the it's cancel even. So you have I in front. Yeah, everything cancels. Just 1 dt. And then this is just I times 2 pi. Okay. So yeah, that one was an interesting problem. But yeah, a lot of these problems work similarly, where you can do some long division and pull stuff out that you know the integral of it is 0, and then you can just deal with a simpler integral, like in this case just 1 over z around this circle, and we found that, and you can show actually that the integral around any circle of 1 over zeta, the integral will always be this same thing, 2 pi I. So very cool that, the circle, it doesn't depend on its radius, and in fact you could, take ovals or really any shape that's a single loop around the origin, right? All right. Yeah, Rex put the Discord in the chat, so we're still chugging along here. Probably gonna have to go in the next 15-ish minutes, so maybe the next problem will be the last one. So yeah, I guess I'll wait for Jake to show up if he shows up at 4. We might want to go over his problem. Seemed like he did a pretty good job on it, but if he has any other questions or any questions about that particular problem. Rex, do you have any questions? Complex stuff? But yeah, I think that was the proper way to do this problem. So just a little bit of long division. Just to recap again, we had an integral around some closed disk of radius 3, I'll just write it like this. And we were integrating this function. d zeta. We applied some long division here to try to rewrite this as like a sum of things. And the idea was that, you know, we have this -1 on the bottom here. We don't know how to deal with that very efficiently. So we wanted to be able to rewrite this as z minus 1 or zeta minus 1 plus 1 over zeta, because that's what we get when we do long division here. We get that this is this times itself plus 1 over zeta. Or sorry, this was this times itself, but then you have a remainder of 1. So yeah. So basically, there, when you do the division, you get this remainder of 1 over zeta here. Then, yeah, and then when we took the integral, we found that it's split, right? And the integral of this first part was 0, and we just solved the integral of the second part was very similar to the one yesterday. It was just 2 pi I. All right, I listed many in our first lesson. In our first lesson? Or in the Discord? I don't see anything. Oh, I'm getting tired. I don't know why. Where am I? Okay. Any questions about these line integrals? Anybody in chat? Anybody just lurking? Oh, in Discord? Which part of Discord? I don't see the questions. All right, I guess we can. Let me just look at Jake's problem since that's already right here in front of me. Actually, yeah, I don't really understand this problem. 2 to the a plus 4 to the a plus 8 to the a is 39. I guess we can just think about this one real quick. It doesn't seem too hard. 8 to the a is 39. I'm assuming, I guess, like a is an integer, maybe? Positive integer? I mean, there can't be that many options, right? I'm not sure how to approach this problem other than guess and check. No, I'm not going to sleep. I have something else to do. Disguised cubic. Oh, are you talking about like the elliptic curve stuff? I guess a would have to be 2 then, right? There's no other option if it's an integer. Oh wait, I guess it's 3 numbers. I'm not sure what the elliptic. What's the Fermat's last theorem thing? 2 to the a will be x. Isn't that just a disguised cubic? Oh, okay, I see what you're saying. Nice. Yeah. So this is like 2 to the a plus 2 to the a squared plus 2 to the a cubed. Or wait, I probably did that wrong. Or no, it's 2 to the third to the a. So 2 to the a to the first power. I don't know. Keep doing the same thing. 2 to the first power to the a plus 2 to the second power to the a, 2 to the third power to the a. I don't know if that helps us though. How does that help us? 2 to the Oh, to the power to a power. No. Oh, is this just 2 to the a plus... Can I commute the powers this way? Yeah. You were right. 2 to the a to the squared. So 2x. Is that right though? Can I do that? All right, I need to think about it for a second, but yeah, I think. Army blood. Could I explain what do you teach? So we teach complex analysis, real analysis, any sort of like calculus classes, multivariable calculus, linear algebra, number theory. We haven't really done too much number theory, but group theory, ring theory, stuff like that. um, I guess this is sort of like number theory. Okay, so this is this just 2 to the a squared though? Yeah, is this just 2 to the a to the third power though? So it's 2 to the a plus 2 to the a squared plus 2 to the a cubed. I guess you can just commute the powers as long as it's not, the power isn't in the exponent, yeah. Okay, so this is really 2 to the a plus 2 to the a squared. Oh, good, yeah. It's 39. Then a is log base 2 of 3. Okay, yeah, but we're not gonna... Oh, okay, I see what you're saying. Oops. Hold on, I set a timer upstairs. I'll be right back. Cubic formula. Yeah, okay, yeah. So yeah, let x be 2 to the a. So this is really just like x plus x squared plus x cubed is 39. So this is like x times 1 plus x squared. So one of the solutions is when 2 to the a is 0, which it never is. So we can divide out by x. Yeah, we can actually divide out by x. Oh, wait, no. Oh, okay, 39. T equals 3? Bring the 39 to the left-hand side to equate to 0. Right. Yeah, but then... I mean, I know there's a cubic formula, but is there like a simpler way to do this? Hmm. Jake's giving us the hard problems. No, I don't think there's a simpler way. Then use cubic formula. Okay, Jake likes giving us these tough ones. Okay, yeah, I don't know if there's an easier way. I mean, you can plug it in the cubic formula, you get three solutions, right? Maybe if there's only one imaginary one, or sorry, if there's only one real one, then that would be the only solution, I suppose. Um, yeah, didn't you say there was only one real one? So then A is, so 2 to the A is 3, or the other plus or minus. So yeah, so 2 to the A is 3, you're saying? So X is 3. So 3 plus 9 is 12. Plus 27 is 39. Yeah, okay, so that looks good. Yeah, so X would be 3, and then, so 2 to the A is 3. So that means that A is log base 2 of 3. Okay. Yeah, I don't think there's a simpler way. I think that's the easiest way to do it. So it's 2 to the A plus 4 to the A plus 8 to the A is 39. Rewrite this as a cubic in 2 to the A. So X is 2 to the A. Now we have a cubic. Find, use the cubic equation or a calculator or somehow solve this equation, and you're going to find that X is 3. That's the only real solution, I think. And then, so 2 to the A is 3. So, yeah, definition, just by definition, we can take the inverse of 2 to the A by applying log base 2. So A is log base 2 of the right-hand side here, which is 3. 6 root both sides and ta-da. Oh, wait, what? What's 6th root? Of what? Oh, 6th root of, wait. What am I missing here? Probably too tired to get this. I mean, when you solve it, I suppose it is plus or minus 3. Oh, yeah, but we don't want the negative one, right? Or actually, the negative one, we can't get a negative solution because X can never be negative. X has to be positive, right? Oh, different problem than what's in chat. Okay. Okay. I don't see Jake in the chat here, so I'm not sure if Jake is showing up today, but yeah, are there any other problems we want to do today? I think this is the last one I'm going to do today. Unless somebody submits a really excellent problem in the next 3 seconds, then, or in the next like 1 minute, then I think we'll just call it for today. But yeah, we'll just continue doing these complex problems. These complex integrals are very interesting, especially to do with this topology algebra type intersection connection between all the different math subjects. But yeah, we're going to get into Cauchy integral theorem and the Cauchy integral formula on Friday. One of the two, I guess, or maybe both. So yeah, that'll make one of the integrals we just solved earlier probably make a lot more sense. The one that we had that was zeta squared over zeta minus 1. That's like straight out of that Cauchy integral formula for a specific function, which I guess was like zeta squared in that case. Okay, yeah, let's just raid Zach, and I hope everyone has a good rest of their week, and I'll see everyone on Friday. Let's see. To the 2I pi. All right. Hope everyone has a good day, and let's go say hi to Zach.